Hello everyone, my name is Shub Patel. My SAP ID is 56, batch B4. I am from third year of electronics from DJ Sangvi College of Engineering. In this video, I am going to show how to design a practical differentiator circuit using opamp OP07 on simulation tool LTspice, and I will also explain its frequency response. So for constructing the circuit, we will first need to calculate the values of resistors and capacitors. So let's move to the calculation part. We have been given that Fa equals to 1 kilohertz and Fb equals to 10 kilohertz. We will first assume C1 equals to 0.1 microfarad. So we know that Fa equals to 1 upon 2 pi Rf C1. So after substituting C1 and Fa, we will get Rf equals to 1.6 kilo ohms. We also know that Fb equals to 1 upon 2 by R1 C1. So after substituting R1 and C1 and Fb, we will get R1 equals to 160 ohm. Now we will assume R1 C1 equals to Rf Cf. So we will get Cf equals to 0.01 microfarad. The offset resistor is a parallel combination of R1 and Rf, and the value obtained is 150 ohm. Now let's move to the simulation software LTspice. I have already constructed the practical differentiator circuit. So this is the feedback resistor, that is 1.6 kilo ohms. This is CF, which is 0.01 microfarad. This is C1, which is 0.1 microfarad. This is input resistor, which is 160 ohms, and this is offset resistor, which is 150 ohms. And this is the input supply uh, uh, supplied to inverting input terminal. So for the frequency response of the differentiator, we will right click over the supply, advance, go to the AC amplitude, type 1 in the box, click on OK. Now right click anywhere on the screen, click on run, go to AC analysis section. In the first box, select decade, second box, type 2000, third, which is start frequency, type 1 Hertz, and fourth, which is stop frequency, type 100 kilohertz. Click on OK. So let's see the input. Let's see the output. Okay, this is the frequency response. This is the frequency response of the differentiator. At for lower frequency, the gain increases constantly. The value of gain increases constantly, and at 1 kilohertz it becomes 0 dB, and at 10 kilohertz it becomes 14 dB. So for different values of frequency, we get different values of resistors and capacitor, and so we get different values of gain, and that's why we can obtain we can obtain different frequency response of the differentiator. In this case, I have taken 1 kilohertz frequency, 1 kilohertz, Fa equals to 1 kilohertz, which is uh, at this particular frequency, our gain becomes 0 dB. And I have taken Fb equal to 10 times of Fa, which is 10 kilohertz. At this particular frequency, our gain is maximum. So initially, our gain increases constantly, and at Fa it becomes 0 dB, and Fb it reaches peak value, and then it starts decreasing after that. So let's move to the differentiator circuit. So basically the differentiator produces the negative differentiation of the input signal. So to verify that, we will apply sinusoidal signal. So for that, first remove this. Uh, right click over here, click on sine, click DC offset 0, amplitude 1 volt, frequency 1 1 kilohertz. Now let's run. Click on run, and then in transient section for the stop time type NNS. So the blue signal, which is this sinusoidal signal, is our input signal, and we have obtained a negative differentiation of this sinusoidal signal. As you can see, this is the green signal is the output signal, which is the negative differentiation of the input sinusoidal signal. And I have already performed for other types of input signal. Let's see its output. I have performed for triangular wave input signal. So for the triangular wave as the input signal, we got a square wave as the output signal. This green signal is the input signal, which is triangular, and the output signal, which is square, which is in blue in color. For triangular signal, we got a negative differentiation, which is a square signal as the output. And I have I have already performed with a square wave as the input signal. For the square wave as the input signal, I got a positive and negative spikes as output. These spikes, which you can see on the screen, is the output, the negative differentiation of the square wave. And this is the frequency response. I have explained it earlier in this video. So in short, at F equals to 1 kilohertz, the frequency becomes 0, and FB equals to 10 kilohertz, which is 10 times of FA. It reaches the gain becomes 0 at FA equals to 1 kilohertz, and at FB equals to 10 kilohertz, which is 10 times of FA. The gain reaches the peak value. Initially, at lower frequency, it was increasing constantly. So let's move to the observation table. This is our observation table. Uh, as you can see, it goes on increasing until FB. The gain goes on increasing until FB, and at FB it reaches the peak value, and after that it start on decreasing again, as you can see here. And at FA, which is 1 kilohertz frequency, it becomes 0 dB. So at FA it becomes 0, and at FB the gain is maximum, which is almost 14 decibel. So that's all for the differentiator uh, in this video, and thank you.